In this class, we are going to introduce the Monte Carlo methods in reinforcement learning. Monte Carlo is an administrative area in Monaco, which is famous for its casino. Therefore, researchers like to use the name Monte Carlo to represent any random-based approaches. So, what is Monte Carlo method in reinforcement learning? It has three features. First, it learns from complete episode. In other words, we need to keep playing the game until game over, get the reward and trace back to and update our value function. Second, it's a model-free method. Unlike dynamic programming, we don't need to know all the states to update the value function. We just play and record the states and rewards we meet. So the Monte Carlo methods are model-free and we don't need the knowledge of MDP transitions and rewards. Third, Monte Carlo uses the average of sample returned to estimate the true reward. Recall this figure, which classify RLO methods based on the width and the depth of update. The previous mentioned dynamic programming update the width of the MDP tree, right? So it sweeps all the states first. On the contrary, the Monte Carlo methods update the width, update the depth first, right? So Monte Carlo method runs the game until the end of an episode, then update the value function backward. Let's review the definition of return and the value function. The return is defined as the total discounted reward. So a return T is the sum of the rewards discounted by the factor gamma from the RT to RT plus capital T. Then the value function is just the expected return of based on the discounted total reward. So different from previous method, Monte Carlo uses empirical mean return, which means it runs the multiple episodes and use the average as the value instead of the expected return. Previously, we used the policy, the probability of policy to estimate the value function of the at the state t. So the main difference between Monte Carlo and other methods are that Monte Carlo uses the empirical mean return. Here is the algorithm of Monte Carlo prediction. There are two kinds of prediction method. The first one is called first visit, and the second is every visit. They are very similar. The difference is that the first visit uses the first visit of state S, the reward, to estimate the value function, while the every visit uses consider multiple visits of same state and use the average of the rewards as estimation. So they are very similar, but in this class we focus on the first visit Monte Carlo prediction. So here is the algorithm. First, we have a policy to be evaluated. Then we reset, initialize the value function and the returns to 0. Then we loop forever for each episode. So we play the episode until the end of this episode. Then we use the end of one episode. And we record the trajectory. Once we have the trajectory, state action reward, the trajectory we update backward. So we look back from the last episode and update our return. So if we find an episode, we find the state is in our trajectory, then we append the return to the list. Then finally we average the returns as our value function. So this is the Monte Carlo prediction algorithm. Now let's apply the Monte Carlo method to a real reinforcement learning problem. The problem that best suitable for Monte Carlo method is the game Blackjack. Here's a picture of a movie 21, which is based on true story of an MIT Blackjack team. The story is about several MIT math whiz assembly a team called MIT Blackjack Team in 1990s and play card counting in Las Vegas casino and won millions of dollars. So after this class, you can train your own idle agent and play the blackjack. Maybe you can bring your agent to the casino, but please take your own responsibility. We won't guarantee that you can make money. Here are the rules of blackjack. So there's one dealer and several players. The goal of each player is to try to beat the dealer by getting a count as close to 21 as possible. So this is why this game is also called 21. So you lose if your total is larger than 21 and you are busted. And the game begins with two cards dealt to both dealer and the player. One of the dealer's cards is face up and the other one is face down. So we have two actions. The first is hit, which means we request additional card. And the second is stick. We stop getting cards if we find our sum is large enough. On the other hand, the dealer has a fixed policy that the dealer sticks when his sum is larger than 17, or it keeps calling, keeps hit otherwise. Blackjack is the game that the player has highest winning probability. So that's why the MIT Blackjack King chose this game. Now let's formulate blackjack as reinforcement learning problem. So the stats are the first the player's current sum from 12 to 21. So that's 10 stat. And the second are the dealers showing cards. The dealer's showing card can be S or from 2 to 10. So it's also 10 stats. And we can use the S as 1 or 11, so there are two different states. The total states are 10 multiplied 10 multiplied 2 equals 200, so the total are 200 states. The reward are first 1 for winning and -1 for losing, otherwise 0 for drawing. So we have two implicit rules. The first, the player will have a fixed policy, fixed strategy. It continues to call until the sum is larger than 12. So if the sum of the player is less than 12, we continue call and get new card. So that's why this is to simplify our states. So we only have player states from 12 to 21. And also the cards are drawn from infinite decks, so the card counting strategy won't work in this problem. So you cannot apply this. You cannot apply your agent to real casino like the MIT Blackjack team in the movie. The state value function of the blackjack will look like this. So if we can use S as 1 or 11, then the fluctuation of the state value function will be larger, right? Which is straightforward. So after 10,000 episodes, we can see that it's still unstable. The state value function are quite noisy. But after 500,000 episodes, we can see the values are quite smooth, and it has high rewards after close to 21, which is intuitive. Then if we don't use S, we just use S as 1, then it's easier to learn. So after 10,000 episodes, you can almost learn the policy for Blackjack. It basically means that we stick if the sum of cards is close to 0, or otherwise we call, right? Then how can we improve the policy? It's actually the same as other method. We first evaluate current policy using the reward from episodes. Then we can use the value function and to improve our policy. So it's the same iteration as other methods. We first evaluate our current policy, and then we improve the current policy by choosing the greedy actions using the latest value function. The only difference is that now we use the sample return. We run until the end of multiple episodes to calculate our value function. There is one drawback of Monte Carlo. That is, if we continue to run the game to the end, there may be many state action pairs that we never visit. So many state action pairs may never be visited. The one solution is to randomly choose the state action pairs at the start of the running episode. It's called exploring starts. So exploring starts is important to simulate and find the reward for different states. So here's the pseudocode of the exploring start. Basically, it's just make sure you select different state and action randomly and run the episode. And the other parts are the same. Once we run to the end of the episode, we update the return backward. Then we add reward to different state action pair. Then we update the Q function of the action state pair. Then finally we can update using the greedy policy, update our current policy. Then again loop for more experience. Here is the optimal policy learned by using the Monte Carlo exploring star method. So from this table, we can see that our strategy, if we can use S as either 1 or 11, our strategy is to hit if the sum of the player is less than 18, or if the card of the dealer is 9 or 10, then our sum should be a little bit higher. But generally, we keep hit if our sum is less than 17 or 18. Otherwise, we stick. If we cannot use S as 11, we use it as 1. And the optimal policy is that largely depends on the dealer's card. If the dealer's card is small, right, then we just stick. But if the shorting card of the dealer is high, then we should hit until our sum is more than 16. So it's more than 17. So this is the optimal policy learned by MCES. The exploring stars is easy for the simulated blackjack game because we can just assign the shown card of the dealer and the sum of the player and then run the simulation. But in practice, we cannot control the start. Usually, we cannot control the start of the environment. So there are two methods based on if it's on policy or off policy that can achieve the same results of exploring stars. The first one is the epsilon greedy, which we choose randomly random actions and follow the greedy policy 1 minus epsilon time and choose the epsilon time. Choose the random action epsilon time. This is epsilon greedy, which we have learned before. The second is off policy method. The off policy has two policies. One is target policy and the other one is behavior policy. We need to develop a strategy to let the behavior policy close to the target policy. The method is called importance sampling. So let's see how to use those two methods to achieve the exploring start. The epsilon greedy method is to choose the greedy action 1 minus epsilon time and choose the random action epsilon time. Here we have multiple actions, so we divide the epsilon probability by the number of actions. So this is actually the number of actions. That is, we choose between equally between all actions except the optimal actions. So that's why we divide the epsilon probability with the number of actions. Otherwise, we choose the optimal action. This is the epsilon greedy. By using the epsilon greedy method, we can achieve the same result of the exploring start and avoid the problem of Monte Carlo methods. Now let's see the second approach. This method is off policy prediction. As we know, the off policy strategy uses two policies. The first one is the target policy, which is the optimal policy that we want to learn, usually the greedy policy. The second is the behavior policy, which is more exploratory and is used to generate behaviors. So the question is how we can update the target policy using the behavior policy. One strategy is to use the importance sampling. So what is importance sampling? Remember that the state action trajectory is actually the multiplications of first the policy and the transition probability. The policy is how we choose different actions. So this is the probability of we choosing action A under state ST. Then once we choose this action, we have some probability that we go into next different state. So we could multiply with the transition probability. Next state ST plus 1. So the trajectory, the state action, reverse state action, is actually the multiplications of the policy and the transition probability. And we can rewrite this trajectory as the multiplication from t to the terminal state, capital T minus 1. So this is the trajectory probability. So the importance sampling is just the ratio between the behavior policy, the relative trajectory probability between the behavior policy and the optimal policy, target policy. So we can use this relative trajectory probability to update the target policy. And there are two strategies that can update the target policy. One is the simple average. The simple average is the relative probability multiplied by the return divided by the number of time steps. So this is the number of time steps, total time steps. Another is the weighted average, which is divided by the sum of the relative probability. So consider that we only visit the stats once in the episode. The ordinary importance sampling is more unstable, while the weighted importance sampling has a lower error rate. So usually the weighted importance sampling is preferred. This is the simulation result in the Blackjack. Let's see a simple problem that can show that ordinary importance sampling is unstable. Okay, this simple problem is we only have one state, and there's a terminal state here shown as a gray square. We have two actions, which is go right or go left. If you go right, the reward is 0. If you choose to go left, there are 0.1 probability that you can go to the terminal state and receive positive reward 1. Otherwise, there are 0.9 reward that you will go back to the state and start again. So suppose now we have two policies, which is the optimal policy should be always go to left, because going right has no reward at all. And our current behavior policy is a random policy that going to left 0.5 times, or going right equally. So our goal is to update our behavior policy and try to approach the true optimal policy. Here is the result of using Monte Carlo first visit algorithm. We have 10 rounds showing different colors. Each round running independently. And we can see that all rounds fails to converge to true optimal policy, that going left, the value of going left is 1. And even so, some policy has infinite variance. This example can show that the ordinary importance sampling is unstable. In fact, we can show that the importance sampling of this simple problem has infinite variance. Recall that the variance can be separated into two terms. This is the formula of variance, which is the expectation of the variable x minus the mean, the square, and the expectation. So this can becomes the expectation of the x square minus the mean square. But the mean is a constant, so and it's a minus term, so we only need to show that the square of the importance sampling ratio and our goal importance sampling ratio goes infinite, then we'll have infinite variance. So let's start calculate. Suppose we go left 1/2 of the time, right? We have 0.5 probability to go left. We go left and we first meet the terminal state and get the reward. We have a 0.1 probability to get the reward, right? So this is our value. Then we calculate the variance using the importance sampling. Alright, using the relative probability of the target and behavior policy. So calculate scale. So this is the first episode. Then second episode, suppose we go back to the state, right? We have 90% of probability to go back to the state. Then again we achieve terminal state. Then in this case we have 2 times of the importance ratio because we have 2 steps. Right? So each step we need to multiply by the relative probability. And continue this process for the depth 3 episode, which has 3 time steps. We go back twice, then go to the terminal step at last. When continue, calculate all different lengths, all different episodes with different lengths, and eventually the sum of all possible episodes can be written as this equation, and this can prove to be to approach infinity. So this is the proof of infinite variance of the ordinary importance sampling.